tons. So it's a huge reactor. Blast furnaces are well developed and again very large in size, and certainly has economy of size, and has been used for a long time, 100, 150 years, or maybe even longer, some of them little ones. But again, with changing conditions and factors, there are issues involved with blast furnace operation. And that is, blast furnace requires coke and also iron ore pellets. Even these fine ores that we generate, they have to be pelletized into balls, because in blast furnace, you cannot charge these powders in the reactor. If you do it, it'll be blown right out of the reactor. And because blast furnace uses coke, essentially pure carbon, so substantial amount of carbon dioxide is produced. And blast furnace itself is very efficient energy-wise. There's very little heat loss and so on. However, to do that, to operate a blast furnace, you have to pelletize again, and also you have to make coke before charging these things in the blast furnace, which requires quite a bit of energy. In terms of the carbon dioxide emissions in the US, this is the US, from various sectors, the total amount is about 6 billion tons from various sectors. Now, in terms of CO2 emission from the US steel industry, total is about 126 million metric tons. That's about 2% of the total carbon dioxide emission from various sectors. So in terms of the percentage, it's a rather small percentage, and but as I said, everybody must be concerned with carbon dioxide emission, and even with a 2%, just 2% emission, I'm glad that steel industry is not only concerned with the carbon dioxide problem, but actually putting in their resources and most importantly, funds, research funds to develop new technologies that will contribute toward solving these carbon dioxide problems. The main motivation for thinking about conceiving this new technology, again, is first the needs for carbon dioxide reduction, but also we expect development of hydrogen economy, and not only the government, US government, but also various private sectors. They're putting a lot of funds and resources for developing hydrogen economy. So we are hopeful that inexpensive hydrogen will be available even to use for iron production. Right now, of course, hydrogen is too expensive to apply towards iron making technology. But as I mentioned, the technology is not solely dependent on the availability of inexpensive hydrogen. We can use less carbon-intensive fuels, such as natural gas, and as I said, even coal. Another factor involved in the development of this particular type of novel iron-making technology is, as I mentioned earlier, the availability in this country as well as elsewhere of very fine iron ore concentrate. How fine? About 30 micrometer or micron size. That's about 1/30th of a millimeter. So these are very, very fine particles, and here I show some micrographs of about 30 micron size iron oxide concentrate. It looks like this. And because the size is very small, there's a lot of surface area per unit mass for reaction to take place rapidly. So the proposed process concept is carrying out the reduction of these fine iron ore particles in suspension with hydrogen as the reducing gas. Hydrogen, although as I mentioned, there are a number of at least 3 different fuels as well as reducing agents that we could think of. Hydrogen would be the cleanest and best fuel and as well as reducing agent. In iron making, fuel and reducing agent, they go hand in hand. The same thing is used for both purposes. And again, the we can use possibly natural gas or even coal. And our target is to replace the currently dominant iron making process, that is blast furnace, BF standing for blast furnace, and BOF is the following step to produce steel. There have been a lot of other alternate iron making process proposed and developed and so on, but none of them is intensive enough to replace a large portion of blast furnace technology. But we're taking, at least we're dreaming about replacing a substantial portion of blast furnaces. This suspension or flash reduction process is not out of the blue. Actually, there is a very similar process being used in copper making, for example. In copper making, the copper minerals contain not only copper, but a little bit of iron, well, not a little, a substantial amount of iron and sulfur. So for copper minerals, when you react these things with oxygen, there's a lot of heat generated. So this process is autogenous, largely autogenous. Don't need much fuel, which is the main difference. Although it looks similar, it's the main difference between the reduction process and this copper flash smelting process. But the fact of the matter is the use of fine concentrate particles flowing with gas and very rapid reaction taking place, it's similar. So this is a bench scale test facility at the University of Utah. It is about 1.5 meters high and 10 inches diameter. Compared with the industrial scale pilot plant, this is a very small unit. However, for a university laboratory, this is a very large and very difficult facility to operate. But again, with substantial support from AISI, we are able to carry out this fairly large-scale test on a university campus, which is very necessary to develop any new technology aimed at developing these big, large blast furnace operations. Just in terms of the fact that the particles can react, can be reduced within a very short time, I show you that within 3 to 4 or 5 seconds of reaction time, we can reach 95, near 100% reduction. And this new process must be, the reaction must, we must take advantage of the rapid reaction of very, very fine particles in order to be competitive with blast furnaces, because we have to produce iron in large quantities. You see around you everywhere there are materials containing iron, so we need to produce this at very high intensity process.